So now we're going to look at some visual proofs of the Pythagorean theorem. It is not enough for you guys just to memorize a equation or a definition. We want you to know where it actually comes from and have a feeling for why it has to be true. To that end, on test day, you're going to be required to do a visual proof of the theorem to show why, if I have a right triangle, the sum of the squares of the legs has to equal the square of the hypotenuse. We're going to be going over 3 such visual proofs, only one of which needs to end up in your notebook and one of which needs to be replicated on test day. Whichever one works the best for you, use that one. So we're going to be using this right triangle for all of these figures. This happens to be a 3, 4, 5 right triangle because Pythagorean triples make our life easier. A, our shortest side, is always going to be represented in red. B, our medium side, is always going to be represented in blue. And C, our longest side, is represented in green. All of these figures are drawn to scale to that particular triangle. So let's take a look at the first one, the one that Pythagoras did. Pythagoras made 2 of these figures. The first one, he took his 4 triangles and he arranged them touching their tips together to form a square in the middle. In the second one, he put the hypotenuses of his triangles together to make a square that looks like this. So on this side, we have a square whose length is A plus B, and whose height is also A plus B. Looking at his other figure, this figure also has a height of A plus B. And it has a width of A plus B. So if both of these figures are squares, with a side length of A plus B. Therefore, these 3 little dots is just a shorthand way of saying therefore. We know that the areas of the big squares are equal. So let's take a look at what makes up the areas of these big squares. Well, this first figure has 4 of the right triangles and has a square in the middle whose sides are each C. Therefore, the area of the square is going to be C times C. It has an area of C squared. That's what it literally means to square a number. What is the area of a square that has that number as one of its sides? So, large square, number 1, its area is equal to 4 triangles plus a square whose area is C squared. So what about the second figure? Well, the second figure is also 4 of these triangles, but it has a small square that has side lengths of A, whose area is A squared, and another square whose side lengths are B. Its area is B squared. So square 2 has an area of 4 triangles plus A squared plus B squared. Now, because the areas of the 2 figures overall are equal to each other, this lets us say that 4 triangles plus C squared has to equal 4 triangles plus A squared plus B squared. if we subtract 4 triangles from both sides, because we can always subtract the same thing from 2 sides of an equation, we are left with c squared equals a squared plus b squared, our Pythagorean theorem. So that was the proof that Pythagoras himself did way back in the day. But that wasn't the only way that people came up with proving that this relationship is fundamentally true for all right triangles. In India, around 1185, they came up with this proof. They started with a square that was c units tall and c units wide. So the initial square has an area of c squared. They put the 4 triangles inside this way, with hypotenuses on the edge. If you do that, it's going to cut out a small little square in the middle, this one that's highlighted in orange. What's the area of this tiny little square, you might ask? Well, take a look at this. The long side of this triangle reaches all the way across the square. The short side of this triangle reaches all the way to the edge of the square and then stops. So if this whole distance is b, and this distance is a, which I can label, then the part that is left over has to be the difference between the two. Or put another way, the small square has a side length of b minus a. Take the whole length b, subtract out the short side a, and you're left with the length of the square. Makes sense so far. But now take a look at this figure over here. All I've done is taken my 4 triangles and this tiny orange square, and I've rearranged them. So therefore, this figure is a rearrangement of the original square. It should have the same area, so its area is also c squared. But let's see what weird sneaky thing has happened here. So this tiny little distance here is b minus a. And then this distance here is a. Well, what is b minus a plus a? Well, if I take b, subtract a, and then add a back to it, this whole thing has a length of b. Likewise, let's take a look here. We have a length of b minus b minus a. What is b minus b minus a? Well, that is the same as a. This side length is a. For the same reason. This length plus b minus a should get me all the way back to b. It's the exact same configuration we had here. That means that this whole figure is equivalent to this one, where we have a square that is a by a, and a square that is b by b. This configuration is the same as the middle one. Therefore, its area is also c squared. If this area equals this area, and this area equals this area, and this area is c squared, then this one has to be c squared. But look at how we've separated out this figure. It is 2 squares, an a squared and a b squared. Therefore, a squared plus b squared has to equal c squared. The last one is a really silly one. This one was actually come up in the 19th century by a guy named James Garfield. Yeah, that James Garfield, as in the 20th president of the United States. About 5 years before he took office, he was messing around, and he came up with his own proof of the Pythagorean Theorem, as people were wont to do back then, I suppose. He decided not to look at squares or triangles, but to look at a trapezoid. Now, one of the key things you need to know is that the formula for area of trapezoid is 1/2 the sum of the bases times the height in between them. The way we define the bases are the two parallel sides that are in a trapezoid, and the height would be the distance that connects them together. So let's see what this looks like if we talk about this trapezoid. So the area of the trapezoid is 1/2, adding the two parallel bases together. All right, so we have an A, and we have a B, so that's just A plus B. And we are multiplying it by the height, the distance that is between them. So that is this distance and this distance. Well, this is also A plus B, because we went A units on this side, and went B units beyond it. So the height is also A plus B. Anytime we're multiplying something by itself, well, that's just the same as doing A plus B squared. Now, if you're really clever, you'll notice, like, oh, right, because this figure is just this one chopped in half. Its area is 1/2 the square A plus B squared. But there's another way we can think about the area of this figure. We can think about it as the area of these two triangles. So we can also think of area of, these two triangles we've been working with, plus this third one up here. So area of three triangles. We have 1/2 base times height for this triangle, plus 1/2 base times height for this triangle, plus 1/2 base times height for this green triangle. The green triangle has side lengths of C and C. So it's 1/2 C squared. So the area of the three triangles is 1/2 of AB plus 1/2 of AB, which is a whole AB, plus 1/2 C squared. Now these two areas should be equal to each other, either the area of the trapezoid or the area of the three triangles. So that lets me say that 1/2 A plus B squared has to equal AB plus 1/2 C squared. I don't like fractions, so I'm going to double everything. This tells me that A plus B squared equals 2AB plus C squared. This is what we call a binomial. And when we square something by itself, we do what's called a binomial expansion. You'll learn more about that in algebra. But for right now, it's sufficient to say that it equals A squared plus 2AB plus B squared. If you're really curious about this, this comes from using what's called the distributive property to FOIL these two things together. Look up FOIL and binomial expansion if you want to learn more. So I've expanded this binomial, and I end up with this gobbledygook down here. Oh, but look, we have a 2AB term on both sides. Those can go away, and I'm left with A squared plus B squared equals C squared. For the test, pick whichever proof makes the most sense to you. Personally, I'm really quite fond of this one up here because it's the most visual and easy for me to wrap my head around. Some people like this one because it is a little sneakier, and some people like this one if they're really good with their algebra. But whichever one works for you, they're all equally true, because the Pythagorean theorem is a fundamental truth of right triangles, not just an equation that we make you memorize.